This lecture is about first order logic or logic with first order quantifiers for all and exists. These are quantifiers or quantification. So the idea behind this for all is literally for all. And you can read this symbol as exists. So with this for all quantifier, now we can express a property like for all objects, some property p holds. Or we can, with this existential quantifier, we can say there is some object for which such that p holds. And why? And let's first discuss why we need this propositional logic. Actually, first the logic. In the case of propositional logic, we had to introduce propositional constant. Propositional constant. So the definition of propositions includes a propositional constant. And this each propositional constant states a fact. For example, we can introduce EQ1 to state 1 is equal to 1. So every propositional constant states a particular fact. But in practice, using proportional constants, using only proportional constant has a lot of problems. So for example, we'd like to usually state that for every natural number x, x is equal to x itself. In the case of proportional logic, there is no apparatus for stating this every. So therefore, we have to introduce proportional constants. For example, EQ1 to state 1 is equal to 1, and we have to introduce EQ2 to state 2 is equal to 2, and similarly EQ3 for 3 is equal to 3. So therefore, we have to introduce an infinite number of propositional constants in order to state a simple fact about natural number. So this is quite impractical. So that's the motivation for introducing predicate and first the quantifier for all and existence. So that's the motivation. To summarize, propositional logic relies on proportional constants. And in the case that we'd like to discuss the properties of many objects, we have to introduce lots of different proportional constants, which is quite impractical. So therefore, we introduce these for all and existence quantifiers along with these predicates, which gives rise to first order logic. So let's discuss the first order logic. So first order logic relies on this notion of a predicate. The predicate expresses some relation between its arguments. Uh, uh, predicate expresses the relation between its arguments. So for example, we could introduce a predicate EQ with two arguments T1 and T2, and we can use this predicate to state a particular relation between its argument T1 and T2, or T1 is equal to T2. And its arguments are called terms. Terms are, you can think of terms as syntactic objects. So in comparison with an infinite number of proportional constants, now we need only this single predicate to state particular relation between all objects or all terms. So instead of EQ1, EQ2, EQ3, etc., instead of this infinite array of proportional constants, we could just use a single predicate to state this equal relation between terms. So that's the big difference between proportional logic and forced logic. Proportional logic uses these proportional constants, whereas forced logic relies on this predicate. And for this reason, first order logic is also called predicate logic as opposed to propositional logic. So we will later, we will introduce this predicate. So this is called, so in this example, EQ is predicate, and it has two argument terms, and combined together, we obtain a new proposition. So for example, we can discuss the truth or falsehood of this statement that T1 is equal to T2. So in order to discuss the syntax for forced logic, we have to formulate the syntax for these terms, because we need these terms in order to introduce predicates. So let's look at the syntax for terms. So terms are defined as, with these meta variables t and s, terms are defined as variables such as x, y, z, blah, blah, blah. And these are variables. And we also have new notions called parameters. Parameters a, b, blah, blah, blah. And we have function symbol f, t1, t2, tn, and as a special case, constant. So these x and y are called term variables. And there's nothing new here. Just like we use variables for integers, we can use variables for terms. So we can define substitutions on these term variables. So, so for example, we could define substitution for these term variables, such as t, where variable x has been replaced by another term s. But the definition is straightforward, because these variables are just placeholders. You can substitute another term for this variable x found inside this term t. That's all. So this is term variables. And the second notion is parameters. And parameters look like term variables, but they are different. So parameters are basically a term, an arbitrary term that we know nothing about. Nothing is a noun about this one. So it's basically a noun, arbitrary term. We just don't know what it is. So we can make no assumption about this term. So we will use the use of parameters later when we actually see the inference rules for the quantifiers. So these parameters almost look like term variables, but they are different because in the case of uh, term variables are just the placeholders. Later, we will fill this placeholder with some concrete term s, something like this. So for variable x, we can actually substitute s. But this parameter, for example, if we have a parameter a, we actually have a term, but we know nothing about it. So we will see, so we will clarify the notion of parameters when we discuss the inference rule. And function symbols, function symbols have this syntax f applied to a certain number of terms. So in that case, this function symbol f has error t. It has error t n because it takes n parameters. And as a special case, suppose that some function c has no argument. In that case, we can simplify, we can abbreviate into this f without these parentheses. So this is called constant. So basically constant is function symbol with 0 argument. So you have to remember that this function symbol, this is a function symbol, this is called a function symbol. It's not really function. So if you have a function, let's say you have function add, it takes 2 integers as arguments. If this was a function, you are supposed to return another object, another term. So for example, this function add would return another object or another term 3. So you are actually converting the arguments 1 and 2 into another term 3. So that's what these functions are. But this function symbol, let's just say function symbol t1, t2, it's not function. So you don't actually reduce the whole function symbol into another term. You don't reduce that because this function symbol together with its argument itself is already a term. You don't further reduce this term into another one. So here's an example. Let's say we use this 0 symbol for constant. It's a constant. And the interpretation, the intention is we'd like to read this symbol for 0. Now you have another successor function symbol. So this is a function symbol. It's not function, and it has error t1, which means that it takes another term as its argument. Now you have a constant and successor function symbol, and we can compose these two, create an infinite array of new terms. For example, successor applied to 0. This is a new function symbol. Function symbol applied to another term. So this itself is a term. You don't reduce it to another term, for example, 1, something like this. You don't do this. There's another example, successor applied to successor of 0. So this is a term, and now this function symbol s has been applied to this term. And remember that this s is not a function, so you don't reduce it. For example, another constant like a 2, you don't do this because this expression itself represents a term. So you don't further reduce it. So now we have finished the definition of terms. Terms are basically some objects that we'd like to discuss using universal and existential quantifiers. Okay, and there are 4 components in the definition. Term variables. They are called term variables, so you can use a substitution. You can substitute another term for this variable. And there's a notion called parameters, and these parameters are actually terms, but we don't know what they are. So we make no assumption about them. And then we have this function symbol, and we have constant as a special case of the function symbol. So one thing you'd like to remember about terms is terms are not proof terms. So terms are basically names for objects. For example, some particular object. Say you have some mathematical notion of 0, and you'd like to represent it with this term. And you have Boolean value true, and you'd like to represent this mathematical notion of a Boolean true with the term true. But this is just an object. You cannot discuss the truth of 0 or the truth of this Boolean value. In contrast, these proof terms are representation of proofs. So these represent proofs, whereas terms can represent any object. It could represent natural numbers, it could represent a Boolean value, or it could represent a tree. So any object can be represented as terms, whereas proof terms are a specific form of objects that are designed to represent the proofs only. Remember that terms are just objects. You cannot discuss the truth of natural number. You cannot discuss the truth or falsehood of trees. But for proof term, you can always find their types, and these types can be interpreted as propositions. So they just belong to different categories. So this is the definition. So this concludes the definition of terms. Okay, remember that terms, you do not discuss the truth or falsehood of terms. You don't have this notion. Terms are just objects. Now we have the definition of terms. Now let's discuss the propositions. So unlike terms, we can actually discuss truth or falsehood of propositions. We, for example, say T1 is equal to T2. And this is going to be proposition, and we can actually try to prove its truth or falsehood. So we can talk about truth or falsehood of propositions, whereas terms are just objects. So for propositions, we use a meta variable a. So propositions are now defined as predicate applied to terms, or we have all these logical connectives, logical connectives from proposition logic. So we inherit all of them, and we introduce uh, universal quantification and existential quantifications. So new to first order logic are this predicate and universal quantification and existential quantification. So this P is called the predicate symbol, and it represents a particular relation between these terms, its argument. So these are all terms, and this predicate symbol represents particular relation between these terms T1 through Tn. So here's an example. Example of predicate P. We can have EQ T T prime to mean that T is equal to T prime, or net T to mean that T is a natural number. So this is a predicate. So therefore, now we can discuss their truth or falsehood. You can try to prove this predicate, or you may never find the proof of this predicate, and so on. And as a special case, predicate can have no argument. In that case, we abbreviate into just the P. So propositional constants are just the special cases of predicates with no argument. So this is the definition of propositions in first-order logic. In addition to all these logical connectives from propositional logic, now we have predicates, which applies this predicate symbol to terms. And previously here, we defined the language for terms. This is the language for terms. And now we have this predicate symbol applied to these terms. And these are two forms of quantifications. And the idea behind this for all A is true for every term x. And existential XA, it means A is true for some term x. Or we can find a term, we can find a term x for which A is true. So that's the idea behind these two forms of quantifications. And we don't actually specify the category or the kind of this object. So in that sense, we are actually talking about pure first-order logic. So when we have this for all x dot A, we don't actually specify the type or kind of x. We don't say We don't say x is a natural number, or we don't say x is a Boolean, or we don't say x is 3. We just say there's some object x, some term x. So later, we will actually extend the syntax so that we can specify the type of this variable x. And that's what type theory is about. And finally, a minor comment about operator precedence. These quantifiers for all exist for all and exist. These quantifiers have the lowest operator precedence. So for example, for all x, A implies B. So you can interpret it either if this for all quantifier has higher precedence than this implication, you'd interpret it as for all x, A implies B. Or alternatively, if this implication has a higher operator precedence, you'd interpret it as for all x, A implies B. And we use this convention because it complies with our intuitive reading of this proposition. So this is not the case. So this has the logic connectives have higher operator precedence than this quantification. And now we have introduced these quantifications. Now we can use variables. This quantification introduces a new variable, term variable. So this is term variable. And this quantification also introduced the new term variable x. Because this x is term variable, it gives rise to several forms of a substitution. So whenever there are variables, we can define corresponding operation for substitution. So similarly here, we can introduce two different forms of substitution. Inside this proposition A, we might have a variable x. So therefore, we can define this substitution. Substitute the term t for this term variable inside this proposition. And inside, we can also find this variable x inside the proof D. So you can also define this operation, which means substitute term t for term variable x inside the proof T. And we can also use another form of substitution. This might be confusing. We can actually substitute the term t for parameter a, because parameter is, let's say we have parameter a. So a itself is a term, but we know nothing about it. It's an arbitrary term. So we actually use this symbol a. So therefore, you can just replace this a with another term, concrete term t. So this is also, we can also define this form of a substitution. We will see uses of this form of a substitution later. So to summarize, terms are defined as term variable or parameters, and then function symbol applied to its arguments. And remember that this is a function symbol, not function. So you don't actually reduce this one into another simpler one, okay? And as a special case, we have constant. So for example, we might have a 0, successor of 0, where this is constant, this successor symbol is function symbol. And with these terms, we can define propositions. Propositions are defined as predicate applied to terms. So these are all terms which are provided as arguments, and this is predicate symbol. And this one combined together, we have this predicate. So predicates, we can discuss the truth or falsehood of a predicate, whereas for terms, we don't have this notion of truth or falsehood. You cannot discuss truth of zero. It doesn't make sense. Whereas, let's say we have equality of zero and successor of zero. This indeed makes sense. Uh, we can actually talk about the truth or falsehood. And we have all these logical connectives from proportional logic, and then we have this universal quantification and existential quantification. Now, let's look at the inference rules. We only have to discuss the introduction and elimination rules for this one and this one. So let's first discuss this for all. Universal quantification for all. The idea behind this one is literally it says for every term x, a is true, a holds. So therefore, you can think of it as an infinite conjunction. Suppose that we have this set of terms. This is the entire set of terms. Let's say we have a term T1. We have term T1, T2, Ti, blah, blah, blah. Let's say this is the set of all terms. Then this for all xa is this property A is true for T1 and also true for T2 and true for Ti. So you can think of it as an infinite conjunction. So if we replace x with T, if we replace x with T1, it's going to be true. So conjunction and T2 x for A conjunction and in general Ti for xa. So this is actually, but we cannot actually write this infinite number of elements for this logic connective conjunction. We have this simplified form for all. So you can think of for all as a simpler way of expressing infinite conjunction. So with this intuition in mind, we can actually formulate the introduction and elimination rule. Let's talk about introduction rule. In order to deduce for all xa, this is introduction rule. You have to actually prove, if you expand this for all quantification in terms of this conjunction, you have to prove T1 xa true, and you also have to prove T2 xa true, and so on. You also have to prove Ti xa true. So you have to have infinite number of proofs in the premise. Clearly, this is infeasible. So the idea here is, instead of this one, the idea is let's introduce an arbitrary term a here. So a is going to be a term. So a itself is a term, unlike term variables. You write the a, and this is actually a term, but we know nothing about it. So you can imagine that there is some unknown arbitrary term, and its name is A. It has a name tag, and inside this name tag, you see A. But we know nothing about this term. It's an arbitrary. So we introduce an arbitrary term A, and then try to prove property A, property capital A, for this parameter A. Suppose that this is true, then you can safely deduce this for all. And in order to indicate that we have introduced a new parameter, now this is a parameter, we annotate this for all introduction rule with A. And the reasoning goes like this. I would like it to prove, for example, every student in this class is smart. I would like to prove this statement. One way to prove this statement is I visit every one of you and then verify that every one of you is indeed smart, which would correspond to proving in this way. But the problem is there are an infinite number of students. There are just infinitely many students. So this is clearly impossible to do in practice. So what I do is I take a random student, random or arbitrary student from this class, and I'd like to call him A, parameter A. So I know nothing about this student A except that he's from this class. That's all I know about this student A. And then I reason about this student A, and then finally conclude that this student A satisfies parameter this property capital A. Then logically we can deduce this property A holds for every student X. This would be logical reasoning that you could employ in everyday conversation. So that's in this way we can justify this for all introduction rule. The elimination rule is pretty simple. For all x, A true. We know that A is true for every term x, so therefore for all elimination rule goes, you can substitute t, any term t, this is any term, for variable x inside A. It's just like one of the conjunction elimination rule applied to conjunction elimination rule applied to particular term t. That's all. So now we have finished the inference rules, developing the inference rules for all. The idea behind it for all is it's infinite conjunction. And the introduction rule exploits this new notion called the parameter. Parameter is a term, an arbitrary term that we know nothing about, that we can make no assumption about. And the elimination rule is just a simple case of this elimination rule for conjunction. You can substitute any term. So that's a conjunction, and now let's discuss disjunction. Existential. Existential x dot A. So the idea is, if A is true for some concrete term for x. So here's an example. Suppose that EQ 0, 0 is true. This is a predicate, this is a term, and this is the same term. Suppose that you have a proof of this one, this predicate. Then you can definitely say EQX dot X is true for some X. Because if you are challenged to present a concrete term for this predicate, then you can definitely present this particular term T. So you can say existence X dot EQX. And similarly to this universal quantification for all, we learned that for all X can be interpreted as infinite conjunction, and similarly, this existential XA can be interpreted as infinite disjunction. The idea is suppose that this is the whole set of terms. We have T1, we have T2, and Ti, blah, blah, blah. So this is the set of all terms. Then the fact that there is some term X for which A is true means that you can actually locate a particular term here which makes A true. So this can be stated as either T1 is such a term, or T2 is such a term, blah, 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 or Ti is such a term. So we see complete symmetry between universal quantification and existential quantification here. Universal is infinite conjunction, and existential quantification is infinite disjunction. Now, in order to prove this one, if you expand this one, if this is true, then you have to actually take a particular branch here, some branch here. Let's say this was the branch, in which case you present a T1. So therefore, you have to, in order to prove existential X dot A, you have to actually provide, you have to actually present a concrete term for this variable X. So in that sense, such a term is called the witness. So this is the idea behind the existential quantification. And now let's see the inference rule. The introduction rule is pretty simple. If you recall the introduction rule for disjunction, if you'd like to prove this one, you have to actually pick up a particular branch, one of these branches. So that means that you find a witness yourself, such as the term T2, and then you can prove, you can show the truth of this proposition. So what that means is, in order to prove existential XA true, you have to find a concrete term, which is called the witness, and then present it. So let's just say you made some effort to find such a term, and you discover that the term is actually T. Then you have this proof. So whenever you have a proof of this form with witness T, you can safely deduce this existential XA. So this is the existential introduction rule. Again, there's nothing new here because you can think of existential XA as an infinite disjunction. Now let's draw the same analogy to develop the elimination rule. What about the elimination rule for what about the elimination rule for disjunction? Sorry, not disjunction, the existential quantifier. So this is existential elimination rule. Again, Let's rely on the intuitive reading of this existential quantification in terms of this infinite disjunction. So suppose that this is the set of all terms t1, t2, blah, blah, ti, blah, blah. This is the entire set of terms. Then, according to the elimination of disjunction, you have to consider infinite number of different branches. For example, the first branch would consider the case T1 is actually the actual witness. And you make this hypothesis, then you deduce true. And in the second branch, you would deduce starting with this hypothesis, you deduce C true. And this goes on and on. And in general, you have Ti for x a true. This is your hypothesis. And then you deduce C true. And then you can deduce C true here. Whichever branch you take, you always end up with a C true, the same truth judgment. So therefore, you can always deduce C true. But this is clearly impossible as an inference rule. So we have to devise some different way of representing essentially the same idea. And again, we exploit the parameter here. Here's an analogy using an example. I'd like to show that there is some smart student here. So this is basically there exists some student X and he is smart or something like this. And I'd like to use this fact, but I don't know who this student is. So what I do is I just assume that the student is A and I know nothing about him. All I know about him is he's smart. That's all I know. So all these infinite number of different branches can be replaced with a single branch that uses this parameter. So here's the inference rule. Existential x a true. I'd like to exploit this one. And I don't know, uh, I don't I don't know the actual witness for this existential quantifier. So I just assume that, but I know that there is a witness. So I assume the witness is an arbitrary term A. So this A is actually the name in the name term of this witness, you will actually see A. But I know nothing about him except that this witness satisfies uh, this property A. So I introduce this new hypothesis. Let's call this W. So this is the existential elimination rule. And I introduce new label. And in addition to this new label, we introduce the new witness. So I also introduce this parameter A. And starting with this hypothesis, I deduce C true. Then I can deduce C true. So that's the existential elimination rule. And one thing to remember here is the scope of this parameter A is limited to this branch only. So you don't want to actually leave parameter A inside the C, in which case it doesn't make sense. So in other words, C must be free of A. You should not find A inside this proposition C. If C contains A, it just doesn't make sense. So for example, let's say there exists in my class a smart student. There is, and I'd like to reason starting from um, this this judgment, this fact. So what I do is I know that exists some smart student, but I don't know who he is. So let me just call him A, call him or her A. So I start with this hypothesis: A is smart, but I don't know who A is. So it's just random, uh, arbitrary student. And then I deduce some fact out of this hypothesis. So for example, then this class is happy. So starting from this hypothesis, A is smart, I deduce another judgment that is irrelevant to A. So for example, this class is happy. Then I can always deduce this class is happy. But suppose that this conclusion included A. For example, A is smart. Well, we start with A is smart, so we deduce A is happy. So what that means is that existential XA, this is there exists some smart student. There is a smart student here. So let me call the smart student A. Smart student is A. I don't know who actually is. So I know nothing about him except that he's smart. And then I deduce then A is happy. Then according to existential elimination rule, I deduce A is happy. Now you see instantly this is nonsense. This doesn't make sense because A is not accounted for. A is supposed to stay inside this hypothesis, this premise. So it is not supposed to escape the premise. So if you find A here, this statement is just nonsense because you don't know where A comes from. So therefore, A should not appear. This parameter A should not appear in the conclusion. So we have seen for existential quantifier, we have seen the introduction rule, and we also developed the elimination rule.